Computers today are more accessible than they ever have been before. They were once a highly exclusive field, but the barrier of entry is being lowered every day. The development of tools and learning aids that lower the skill floor has allowed virtually anybody who wants to learn computers the capability to do just that.
However, this goes both ways. As much easier as it is for someone to use computers, it is also that much easier to attack computers. This is an inevitable development. Computers are designed to do exactly what the user tells them. They're just machines. They can't think. But the fact remains that it is now easier to harass other computer users than it ever has been.
To demonstrate this point, we've endeavored to create malicious software as any non-tech aficionado would, in an easy-to-write language. We decided to write in Python, which is known to be a very easy-to-learn language. Python is also heavily documented online, meaning that anybody would be able to write the programs that we have.
But first, let me do this real quick. Oh, I can feel the power already. Before we dig into the actual project, it's a good idea to talk a bit about the status quo. Malicious Python code isn't unheard of. Any web search for Python malware or malicious Python code will bring up a few results. In 2021, Ars Technica reported on libraries on PyPy that contained malware, stealing personal info from users who downloaded the package. 2023 saw another malicious Python package that hid its own ill intent by presenting some of its content in differing Unicode formats, helping it to avoid automatic detection as reported by Bleeping Computer. Also in 2023, cloud security company Wiz reported on a Python program which they had found, which hijacked cloud resources to use for crypto mining. They dubbed it Pylus. So as you can see, there's clearly a precedent for Pythonic malware. So the question is, why isn't everybody doing this? Well, there are a few factors to take into account. First of all is that in its base form, Python code cannot be run without the Python interpreter. You may have noticed that the majority of news stories that came up on those web searches are about malicious Python packages rather than actual malware programs. The reason why is the dependence on the interpreter. Not everyone is going to have a Python interpreter, especially not the technologically illiterate who are most likely to fall for a malware attack in the first place. As such, your main targets are likely to be Python authors. The dependence on the Python interpreter does more than just reduce your audience. Having your code in Python means that it's very readable, more human readable than in most other programming languages. That means that the reverse engineering phase of malware analysis is as simple as opening the file and reading it. Obfuscation is certainly possible in Python, but it's more difficult than it is in other programming languages. There are ways around this requirement for an interpreter. PyInstaller is a program that packs Python code into distributable exe files, and other such solutions exist. But at that point, you might be better off writing your malware in one of the real programming languages like C or even assembly. It'll likely make your malware files more lightweight, you'll have more control over the minutiae of operations, and you'll more likely be able to find tools that can help you obfuscate your code.
Okay, for my section, I will walk through a small educational project where I built a basic keylogger using Python. The goal was to understand how keystroke monitoring works, what risk it presents, and how simple it can be to replicate malware behavior using common tools. This helps us think more critically about system security and defense. This is a breakdown of how keylogger works. It uses the pinput library to monitor keyboard input in real time. Every key that's pressed gets written into a file called log.txt. The script also includes a persistence feature. It modifies the Windows registry to automatically run itself whenever the system starts up. All of this is handled through event listeners that keep the script running and capturing without user interaction. This is a screenshot of the log.txt file where the captured keystrokes are stored. Each key is recorded the moment it's pressed, including letters, numbers, and even special keys like enter or space. This shows how even a simple script can collect sensitive data silently, like passwords or messages, with minimal effort or system access. To make the keylogger run automatically every time the computer starts, I added it to the Windows registry under the Run section. The script registers itself under the name System Update, which makes it look harmless and blend in with real system processes. This is a basic form of malware persistence. It allows the program to survive reboots and stay active without the user's knowledge. You can see the registry entry in the screenshot showing the path to the keylogger script. In malware analysis, keyloggers fall under the category of information stealers. Their behavior can be observed through dynamic analysis, especially in sandboxed environments. Registry-based persistence, like the one we used, is a clear host-based artifact that analysts use to identify and trace malware. By building this ourselves, we better understand what to look for in real-world samples. As analysts, we focus on signs like unexpected startup entries in the registry or scripts accessing keyboard inputs. If we saw a file like log.txt being updated frequently, we would investigate that. Since Python-based malware is easy to modify, static signatures often miss it. That's why behavioral analysis and sandboxing are critical in detecting these threats. Thank you.
For my section, I opted to go fishing and pick up some keys while I was out. My premise was simple: a killer app that secretly logs keystrokes. Obviously, I couldn't make anything too cool with the timetables we were under, but I did whip together this little top-down game. The visuals are stolen from a Disney movie because I'm evil. We play as this tank and navigate a randomly generated canyon. The goal is simple: get from one end of the canyon to the other without touching the walls. Touch the walls 5 times, it's game over for you. I wanted to add proper enemies, but I didn't have time on account of I have 2 papers to write this week syndrome. Did any wonder I'm so evil? The tank base follows the player's movements, and the tank head follows the mouse cursor. A score goes up the more levels the tank clears, and this is stored, allowing for a high score. This is mostly a proof of concept. With more development time, a more finished game could be developed, and many more users could be led to download it. Wouldn't want to miss out on a cool new app after all. But all of that is just a cover story. The game uses this long string of characters as a hackneyed RNG system to generate our canyons for our levels. But this string holds a secret. It's actually the hex values of an executable file. This is the heart of the trick. Whenever the player clears a level, it writes that string to a new file and tries to set that file up as a startup process. That way, when the user restarts their computer, the process will start as well. The startup process is set up via the registry, which we're already accessing to store that high score. The variables in the program that have to do with our malware injection are intentionally given misleading names to try and keep the user from immediately knowing what's going on. The executable file in question is a keylogger, written in Python and turned into an executable with PyInstaller. The actual logger is very basic, and I actually wrote it in about a day. Utilizing the PyInput library, sound familiar? It records user keystrokes. Then, it uses the time module and the sockets module to send those keystrokes back to my computer every few minutes so I can analyze them. It also checks whether my computer can actually be reached, and if not, it disables logging for 30 minutes to decrease suspicion. This system can allow me to see passwords, Google search terms, personal conversations, and more as they're typed out. Admittedly out of context, but over a long enough time or a short enough time, it would get the job done, I think. This is what we in the malware business like to call a live demo. Here we've got a simulated victim machine, and we're going to see how our malware could affect it. So, we have ourselves a victim who has installed this full game written in Python. All he has to do is run this file, paranoids.py, and all the magic happens. Now, in order to see what's going on, we got to get to the end of the first level. So just sit back and watch the master at work. Alright, now that we're at level 2, we've got everything we need to. So we'll close the game now. And you'll notice that this backup folder is created. If we check in here, we can see an executable, WinSecureServe. But the real stuff happens when we check out the registry. First off, I've already gotten to the correct directory in the registry. You can see this address at the top here. And look down here, Windows Security Services, with the address of our executable file. We can also scroll up here, if one wishes. Check out Evil Softworks. Click in here at score, and wouldn't you know, thanks. And there's our score. Who'd have thunk? Over here on my master control PC, I just have to set up my server, Python log server.py, and it's ready to accept connections to the victim. Back over here on our victim PC, all we have to do is shut down and restart our computer, and we'll see exactly what happens. With our computer restarted, we'll just log into our account. And we'll check the task manager to see what's going on. And wouldn't you know it, WinSecureServe is running as a background process. All we have to do is wait for input to come through the network. Hopefully shouldn't take long. So, how's the wife? Okay, full disclosure, I put in the wrong IP address when I wrote the code for this. Probably would work if I had the right one, but this code takes several hours to convert, so we're just gonna pretend like it worked and move on. Thanks. There's a lot more that could be done that can make this program even more advanced, or tweak its functionality. First off, we could get our program set up as a service rather than just as a startup program. According to my spy network, this would require one of two things. For the program to have been explicitly written as a service, which, given the current tools for Python, is not really feasible, or for the victim computer to have access to the NT resource kit, which obviously isn't going to be universal, though an if-then statement could potentially check if that was the case and decide what to do then. For this project, I chose to eschew functionality on Linux distributions entirely. Torvaldians tend to be a little bit more savvy anyway, so they just get to play the game. The keylogger itself could be made much more advanced. In theory, we could also capture mouse movements or network packets, and even take screenshots to send back to the server. We could run our finished Python code through PyInstaller to get a PE or ELF file, which would make it harder to reverse engineer and further cloak our true intentions. The server program, as of now, can only accept one connection at a time. However, it could be rewritten with multi-threading in mind so that multiple keyloggers could be reporting back to the server all at the same time. Finally, it's worth mentioning that this was never tested outside of my home LAN, and additional steps may be required to make it work over the internet.
Hello, my name is Blake, and for my part of the project, I decided to do a process replication slash worm sort of thing built entirely within Python. And let's just jump straight into it, not waste any time here. All right, so As you can see, I tried making it as configurable as possible. Here we have the max instances. This is how many processes will be running at a time. This can get a little finicky, which I will talk about in a minute. The sleep range is basically how often the processes will pull how many instances there are currently running. So right now I have it set to a pretty short duration. This is 2 to 4 seconds, and it will pick a random time within. I wanted to pick a random time within because a worm would normally not go off of a designated time, like every 30 seconds or something like that. It would be preferably random, so it'd be harder to see running. And yeah, this is actually what kind of causes problems with the max instances. There are times in which the processes will pull for how many instances are running, and if one has been deleted, both more than one process may notice that there is less than 5, and then they will all make a process. So then you'll go over 5, which isn't that big of a deal. It's just you'll have padding of removal until you start getting below 5, which it'll start replicating again. Moving on, terminate.flag is what we use to stop our worm from running any further. Replication log, we just have a simple log, as you can see here. It just writes down the time and then what happened. Again, pretty simple. And then our base payload we have as, if I can pull it up real quick, just a picture of my cat. His name is Wallace. He'll be our payload for now. Normally this could be something malicious, like a keylogger, like a Bitcoin miner perhaps, anything. But for now, we just have it as a PNG. And I don't want to get too bogged down into the details, otherwise this video will be much longer than it needs to be. But here's the main execution. Basically, when it first gets ran, we'll make a parent process, which will be our initial one. As you can see, we first check and make sure that we don't have our flag. If we do have our flag, we'll go here. Pretty simple. It just deletes all of our processes and the files that they may have made. Pretty interesting. And then if we also don't have a base payload, it'll also exit. Otherwise, we will make a duplicate of our payload, and then we will start our loop for the rest of the processes. Again, we're going to be checking and making sure that we don't have the flag, and if we do not, we're going to continue on through, and if we are below the max amount of instances that we have, our processes will duplicate and make new ones, which will make new files, and yeah. So let's see it in action, shall we? Let me open this up. And before we actually get into it, here, I just want to show you what's in the log right now. Right now we don't have anything. I wanted it so whenever the flag was made, it would clear all proof and evidence of things going on, and so we only have this. Yeah, so let's first get rid of our flag, and then let's run our program. Pretty simple. We just run it like that, and you can see immediately our stuff starting to get populated, and you also see the timing issue I was talking about. Again, if you had more time between, this will be less likely to happen, but for now it's all right. And again, these are just duplicates of our payload that we initially had. And normally a worm would try and put these in random places within your PC. That way it would be harder to find them, and if you do find them, it may be bit harder to figure out where they're coming from. But let's take a look at what's going on here. We're going to use this command to just look at the processes currently going. As you can see, we are over 5 right now. So what we're going to have to do is, oh, hold on. Actually, before I continue, let's look at the log. The log, obviously, as you can see, this right here is where it detects at the same exact time, and then makes an extra one that we don't need. Yeah, log's working just fine. Let's kill some of these. I don't feel like typing it all, so I'm just gonna do this. 7712, get rid of. And then pay attention to the folder on the right, because that will show when we introduce new ones. Because right when there are new ones, well, you just saw right there. Which one was it? It was this one right here. Yeah, this is our new one. And yeah, so it'll just keep doing this. It doesn't matter how many you, oops, I just duplicated the same one. It doesn't matter how many times you delete a process. There will always be more going until you decide to put in the flag. And let's do that right now. Pretty straightforward. Just make an empty file with the name. It's my bad. Yes, please. And boom, as you can see, it deleted everything we had there. And also within the log, it's all gone. And yeah, that's pretty much all there is to it. Again, if this was a malicious program, we wouldn't be having these logs, and they wouldn't all be in the same folder. But just for testing sake and for the project, I decided it should just all go in here. But yeah, that's what Python could possibly be capable of. And yeah, that'll be all. Thank you.
3 projects, and we think these convey the point very well. These aren't necessarily the best malwares on the market, but they don't have to be.
First of all, we were doing this for demonstrative purposes. Frankly, our programs are pretty tame, mostly there to demonstrate the ideas at play. If we were really trying to screw someone up, we could do stuff that was way worse than what we currently have.
Secondly, there's quantity to keep in mind. While these may not be the most effective programs in a specific instance, the fact we were able to turn these around in less than a semester shows how quick Python is able to work. Even disregarding the fact that more dev time could allow the programs to be more effective, the quick turnaround time allows for malware developers to crank out malicious programs incredibly quickly, like we have.
This should serve not to make us panic, but to make us aware. Malware is going to become more common in coming days, and it's very likely to come from all sorts of places and levels of computer experience. As the bar of entry to computer use drops, more riffraff is going to come through every day. So be on guard, because the next malware attack could come from anywhere.